Okay, introductory to probability. Probability is a measure of the likelihood of a random phenomenon or chance behavior. Probability describes the long-term proportion with which a certain outcome will occur in certain situations with short-term uncertainty. Probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. In probability, an experiment is any process that can be repeated in which the results are uncertain. The sample space S of a probability experiment is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. We will denote the events of one outcome, sometimes called simple events, E sub I. In general, events are denoted using capital letters such as capital E. Here's an example. Consider the probability experiment of having two children. First, we're going to identify the outcomes of the probability experiment, then determine the sample space, then define the event E, capital E, which is have one boy, and also define a separate event, capital G, which is have at least one girl. So the first one, identify the outcomes of the probability experiment. Here they are. E sub 1 is that the first child is a boy, the second child is also a boy. Another simple event, E sub 2, is that the first child is a boy and the second child is a girl. The third simple event is that the first child is a girl and the second child is a boy. And finally, the final simple event is that the first child is a girl and the second child is also a girl. Note that the middle two values are distinct. Boy then girl is different than girl then boy. In a situation like that, it's clear to any observer that there is a difference between them. In E sub 2, the boy came first, therefore he's older than the girl. And in E sub 3, the girl came first, therefore she's older than the boy. These two are clearly two different events. In all, these are simple events, and these are all the simple events of this particular type of an experiment. So for part B, determine the sample space. The sample space is the four possible outcomes we just outlined. The first one being boy-boy, the second one boy-girl, the third one girl-boy, the fourth one girl-girl. We can denote it this way, where we spell it all out, separated by commas, or since we already used the notation of E sub 1, E sub 2, E sub 3, and E sub 4, then we can use this shorthand notation to describe the exact same sample space. Define the event E equals to have one boy. Okay, so now we have a compound event. A compound event is a collection of simple events. In this case, have one boy can be achieved by either this case, first have one boy, the first child is a boy, the second one is a girl, or the other case where the first one was a girl and the second one was a boy. Again, we can either denote it this way, spelled out, or we can use this shorthand notation, which makes light of our definition of E sub 2 and E sub 3. Okay, so this is an example of a compound event. Another compound event is capital G, which is have at least one girl. So capital G equals to boy, comma, girl, girl, comma, boy, or girl, comma, girl. All three of these events satisfy the compound event of have at least one girl. And again, we can also take advantage of this shorthand notation of E sub 2, E sub 3, E sub 4, as long as we remember what the definitions were of E sub 2, E sub 3, and E sub 4. Again, this is another example of a compound event. All of these were events. This is a compound event. This is also another compound event. And these were simple events. They're still events. All of them are called events. Rules of probabilities. There are two really important rules of probability that we must always bear in mind. The first one is that the probability of any event E, noted as P of E, must be greater than or equal to 0 and less than or equal to 1. That is, that P of E must land between 0 and 1, noted this way with two inequalities. Okay, so this means that there are no probabilities that are below 0. You can't have a negative probability in statistics. And there cannot be any probabilities that are greater than 1. There is no such thing as a probability being greater than 100% in statistics. The second rule is that the sum of the probabilities of all the outcomes must be equal to 1. That is, if the sample space S equals to E sub 1, E sub 2, dot, 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 all the way out to E sub n, then if we calculate the probability of E sub 1 and the probability of E sub 2, so on and so forth, for all the events in our sample space, then the sum of those probabilities should be equal to 1. Please note that we are talking about simple events in this case. The sample space is made up of all the simple events, not the compound events. So it should make sense that when we find the probability of each one of these and add them, they should add up to 100%, because if we apply this experiment one time, exactly one of these must happen. Therefore, the sum of all their probabilities must be equal to 100%. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules probabilities. Here's an example. If a bag of peanut M&M milk chocolate candies, the color of the candies can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. The table shows each color and the probability of drawing the color. Verify that this is a probability model. So what we have here, this table shows on the left all possible outcomes, the various colors of the candy, brown, yellow, red, blue. Notice that there is no purple, for instance. Purple is not on here because it's not one of the possible colors of the M&M candies. On the right-hand side, we have the probability associated to each individual color. So if we randomly select one M&M peanut candy, the probability that it is going to be a red one is 12%. If we randomly select one M&M candy, the probability that it is green is going to be 15%, and so on and so forth. So if this is a true probability model, it must satisfy our two rules. The first rule being that each probability must be between 0 and 1, and that is satisfied by each and every one of these listed probabilities. There are no negative probabilities and there are no probabilities over 1. Okay. The second rule is that the sum of the probabilities must add up to 1, and that is true. So all probabilities are between 0 and 1 inclusive. And because if we add up all these probabilities that add up to 1, that means that this is a proper probability model to describe the color breakdown of M&M chocolate candies. More notation. If an event is impossible, then the probability of the event is said to be 0. If an event is absolutely certain, then the probability of the event is said to be 1. An unusual event is an event that has a low probability of occurring. A rule of thumb in statistics is that an unusual event is something below 5%. There are three main methods for which we will calculate probability: the classical method, the empirical, also known as the experimental method, and the subjective method. First, let's focus on the classical method. The classical method of computing probabilities requires equally likely outcomes. An experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. That's really important. That's a very important distinction between the various methods of computing probability. So for the classical, this is very important. Each simple event in the sample space must be equally likely of occurring. Computing probability using the classical method. If an experiment has n equally likely outcomes, and if the number of ways that an event capital E can occur is m, then the probability of E, P of E, is a fraction where the numerator is the number of ways that E can occur, and the denominator is the number of possible outcomes. In this case, m divided by n. Likewise, we can use a different notation, P of E equals to N of E divided by N of S, where this capital N represents the number of outcomes in E, and the capital N of S represents the number of outcomes in the sample space. We get the same result of M divided by N.